Alright, concavity. So if we're going to find and justify intervals where each function is concave up or concave down, as well as the points of inflection, we need to make sure we find the second derivative of each function. Probably best to start off with continuity so we don't forget. F is a polynomial, so f is continuous and differentiable. I don't think our derivative is going to be terribly difficult. 12x cubed minus 12x squared minus 12x plus 12. And then f double prime is 36x squared minus 24x minus 12. So we're going to let f double prime of x equals 0. F double prime is always defined. We probably can't do this in our head, but I might as well factor out a 12 while we're at it. So we have a little bit easier. 3x squared minus 2x minus 1. And we can drop that 12 as well. Let's see, that's going to be a 3x, an x. Okay, so when our factor is positive, negative, the negative is going to be over here, because 3x times negative 1 is negative 3, plus x is negative 2x. Okay, so let's see, x equals negative 1/3, x equals 1. So we need a sign chart. This is the sign of f double prime of x. Negative 1/3, 1, these inputs are x's. We could be fun and change colors. Alright, so when I choose a number larger than 1, like 10, 3x plus 1 is positive, or 3 times 10 plus 1 is positive, 10 minus 1 is positive, positive times a positive, f is concave up for x values greater than 1. When I choose a number in between negative 1/3 and 1, like 0, 3 times 0 plus 1 is positive, 0 minus 1 is negative, positive times the negative is negative, and f is concave down. We assume we're going to get a negative f double prime for very large negative numbers. 3 times negative 10 is plus 1 is negative, negative 10 minus 1 is negative, negative times the negative is a positive. Okay. So, justification, f is continuous. Let's see, f double prime of x is greater than 0 on negative infinity to negative 1/3. Now that's a little ugly. And on 1 to infinity. So f is concave up. I could say on those intervals, but I think I'm just going to restate those intervals. Remember, with concavity, always open endpoints. F double prime is less than 0 on negative 1/3 to 1. So f is concave up on negative 1/3 to 1. And we need to do points of inflection. You might think you have enough justification here, but you really have to kind of dot your I's and cross your T's, so we'll just say f double prime changes signs at x equals negative 1/3 and x equals 1. So g of x, wow, where'd g come from? F of x has points of inflection at x equals negative 1/3 and x equals 1. Okay, I think that's pretty straightforward, but that was a polynomial, so let's find a harder one. 2024 kids said I shouldn't have everything in the solution guides. It makes things too easy. Well, inverse sine isn't memorized by most of my students anymore. So inverse sine is the inverse of sine, and instead of containing the point pi halves 1, it contains the point 1 pi halves, -1 negative pi halves, and inverse sine of x looks like this. So we should expect g double prime to be negative from -1 to 0 and positive from 0 to 1. Okay. Ooh, do some work in black. So, turns out g is continuous on -1 to 1. We're going to have the first derivative, 1 over the square root of 1 minus x squared. We're going to have that memorized. If we want to do the second derivative, it's probably easier to rewrite this so we can use the power rule instead of the quotient rule and just a little bit of chain rule. So g double prime of x, move that -1/2 out front. -1/2 of stuff to the -3/2. That stuff is 1 minus x squared, which has a rate of change of -2x. So g double prime of x. So let's see, the 2's and the negatives will be divided out. We'll just have an x in the numerator, and 1 minus x squared is square root raised to the 3rd power. Okay, so I like this form. G double prime of x equals 0 when x equals 0. That's when the numerator equals 0. G double prime of x is undefined when that denominator is equal to 0, and that's positive and -1. Hopefully you can see on the graph, if I've drawn it semi-accurately, it seems like we could draw tangent lines, and we can, but those are vertical tangents, since it's the graph of sine of x. Has horizontal tangents at pi halves and -pi halves, because really we're looking at that part of the graph. Alright, sine chart. Bars at the ends for -1 and 1. These are x's. We're talking about the sine of g prime. Nope, g double prime. 0 in the middle. And let's see, an x value between 0 and 1, we can just think a positive number. 0.1. 0.1 makes the numerator x positive. 1 minus 0.1 squared is positive, and the square root of that would be positive, cubed would be positive. And let's see, that does match. We expect to have inverse sine to be concave up from 0 to 1. I'm assuming negative here, but let's make sure. -0.1 in the numerator is negative. 0.1 squared is 0.01. 1 minus 0.01. Okay, that is going to be positive denominator, negative numerator. So concave down, concave up. Change the color because why not? Okay, so g of x is continuous. Oh, we should... g of x is continuous on -1 to 1. G double prime of x is less than 0 on -1 to 0. Open endpoints. We can't include -1, remember. That's where g double prime was undefined. Anyway, so g is concave up, concave down. Concave down on -1 to 0. G double prime of x is greater than 0 on 0 to 1. So g of x is concave up. on 0 to 1. G double prime of x changes sign. At x equals 0. So g of x has a point of inflection at x equals 0. Okay, I think I'll make some more, but my handwriting's getting sloppy because of talking, I guess, so I'm going to do the rest quietly.